Okay, good. One mic study. Excellent option for US. Good.
So you guys all survived the election, evidently. Realizing that pollsters don't necessarily get it correct. How many people here are Americans? What? So did you vote? Was that an easy process, or is it kind of difficult?
Yeah, they emailed it to me. I emailed it back. It was all done in like 5 minutes.
Oh, okay.
I just signed away my right to receive the ballot. Other than that,
Well, irrespective of which president there is in the United States, they're not going to change the fundamentals of electromagnetics. So you're not out anything on that. Okay, what I want to do today is to kind of finish up the technical aspect about electromagnetic induction. So there's two lectures, the one that we had on Monday and the one today, that really probably consolidate, almost as much material as you do in some of the rest of the course, because there's just quite a few things happening. But just like magnetics, if you look at it as a whole thing, things become kind of complicated. But if you just pick it apart piece by piece, you start to see like, oh, okay, now I've got to kind of understand it. So I want to go through again. I'm going to summarize a little bit what we did on Monday. And for those people who went to the lab, actually, I wouldn't mind finding out. So for the people who went to the lab, were you able to kind of consolidate the material from the lecture into the lab, and then by the time you got out of the lab, sort of feel like, okay, you know what's going on, or still mystified? Anybody? Who did the lab on Monday? Okay, so what was it like at the end of the lab? Did you start to feel like you kind of knowing what's going on, or?
Yeah, it was pretty reasonable. Get help put it all together. There's still some obviously similar learning too, but
yeah. So I think it's like anything else that's got a number of pieces to it. The first time you see it, it's like, whoa, wait, is that? And then you see it the second time, and then you say, oh, okay, I'm starting to get it. And then by the time you see it the third time, it's like, oh, of course, why is that? So here's the here's the basic elements. We need to have a time-varying magnetic field. That generates for us an electric field everywhere. If that electric field happens to be in a place where there's a good conductor, then there's going to be currents that are set up. That's called Ohm's law. So current density is equal to conductivity times electric field. And once we have these currents that are set up, then those currents give rise to magnetic fields. So every time you have a current, you always have a magnetic field that's associated with it. And you can always get a sense about the direction of that field by that right-hand rule. So what we were looking at is the following. We've got a transmitter, which is just a loop of wire with a generator attached to it. So there's a harmonic wave that goes in there. It's a sinusoid. So that, of course, is going to give rise to a time-varying magnetic field. And that magnetic field comes down and it impinges upon some target here. And the thing that was really important about what happened here was something called the coupling. And the other thing was the flux. So the flux was the normal component of B. So if we have a loop here and we've got a magnetic field coming out like this, then the flux that comes out is just the normal component of that times whatever the area is. So that if the loop is like this and the magnetic field is coming out like this, then it's just the strength of B times the area. But if the loop is like, well,
Doug, I think the chalkboard.
maybe that's better. If the loop is like this and the magnetic field is like this, so that it's parallel to it, then there's no magnetic field that's cutting through. So therefore, you know, B dot n hat, so n hat's this unit normal from here, dA is just, you know, equal to 0 in that particular case. When this is not equal to 0, then the electromagnetic force or the voltage that is produced through that is just the time rate of change of that magnetic flux through there. So an important component here is going to be this transmitter, and then how that flux impinges upon the target. So this was a picture that we showed last time. So if we imagine that we've got some kind of coil of wire here, so that gives rise to magnetic fields like this. If the target loop is sitting here, there's a lot of flux that's going through, so you're going to get a great big current that's going to be generated here. On the other hand, if your target loop is like this and the magnetic field is like this, then there's no flux that's going through there, so you're not going to get any currents that are induced. So depending upon the orientation of your target compared to that incident magnetic field, you're going to get different amounts of currents that are induced. If we put everything together, we've got a transmitter loop, we've got our target, and we've got our receiver. What we're ultimately interested in, and this is going to be the data, is this secondary magnetic field at the receiver compared to what the primary field is at the receiver. So it's going to be this kind of a ratio. And that depends upon quite a few things. The important thing is how everything is coupled. And when you do the lab, you're going to see a term that looks like this. These quantities here, L, are just, they're called a mutual coupling coefficient that connects loop 1 with loop 2. So in this particular case here, with loop 1 like this, there's lots of flux that's coming through here. When this is oriented like this, this coefficient is actually going to be pretty large. If this loop was oriented differently, so let's suppose it's almost horizontal, then there'd be no flux that's going through. In that case, L12 is really small. So these coupling coefficients depend upon sort of the relative orientations of the transmitter and receiver. And you have the option in the lab of kind of adjusting these guys to have greater or lesser amounts of flux. In the end, it's kind of a multiple sequences that's going on, because we've got the flux from the transmitter coming in here. Good, so that's this L12. But now we also have to connect whatever currents are going on in here with this loop back in here. So if I've got magnetic fields that are produced by here, and there's a lot of flux lines that are going through this loop, then I'm going to be good to go. I'm going to have good signal. If that loop had been at a different geometry, then I wouldn't get so much signal. So the strength of what we're going to get here depends upon the coupling between the transmitter and the target, and also between the target and the receiver. and that's what gives this guy. And then we're dividing it by the primary field, and that depends upon the coupling between the transmitter and the receiver. So there's a direct signal that's just going, a primary signal that's just going from the transmitter to the receiver, as well as this guy. Okay, so that was the first part, and we're going to come back at that, and we're going to sketch out what happens as we drag this system over top of a pipe. There was also another term, and I don't want to get into the details of this guy here, but this is really dependent upon what we have for a target. It depends upon what frequency we have, and what kind of the resistance and the inductance of the target. So for what we care about is just sort of a picture of what this guy looks like. And that's what we show here. We have on this axis here a response. On this axis, we've got that parameter omega L upon R, or alpha. And as we go up here, this quantity is getting bigger, so we could have higher frequencies, or we could have lower resistances, whatever. And we go down the other way, we get values that are small. The important thing here is that there is a blue line that constitutes what we call the in phase, or the real part. Did you have a question?
Yes, I'm just wondering what that L is. It doesn't have a subscript. Is that to do with the length as in perimeter of the loop?
No, that's just the inductance of the loop. Remember, we said that we're going to have it as a circuit, so that circuit, it's got a resistance and an inductance. So the only things that are coupling are these guys here, and that's just the initial L. So the blue line represents what we're going to call the real component, which is the component that's in phase. So remember, the secondary field has got, it's still harmonic, and then I was trying to diddle around with my hands last time. Things that are in phase, would kind of go like this. So that's the real part. So anything that comes back is harmonic. Some of it is going to be looking just, you can break it into two parts. There'll be a certain amount that is in phase with this, and then there's a certain amount that's out of phase. The in phase part is governed by this blue curve, and the out of phase part looks like this. So at very low frequencies, the out of phase part, or quadrature part, or imaginary part, all the same words, or different words for the same thing, are much larger than the real. At very high frequencies, the real part dominates much larger than the imaginary part. Okay, so now we can put all that together with one more thing, and that is we're going to plot this quantity Hs upon Hp, and we need to have a sign convention, and our sign convention is going to be the following. If we're always going to have at the receiver a primary and a secondary field. If the primary and the secondary are pointing in the same direction, we're going to say it's positive. So they could be both going up, or they could both be going down. That's fine. We're just going to plot that number as a positive number. If they're in opposite directions, we're going to say it's negative. So if the primary is going up, secondary down, or primary down, secondary up, they're in opposite directions, so it's a negative value. Okay. Here's our situation. We've got a pipe, and we've got our instrument we're going to move over this pipe, and we're going to sketch out this curve. And the important parts is there's a positive part, there's a negative part, another positive, and there's two zero crossings. So here's your EM31, transmitter, receiver. And at the very first part, and I want to break this down into two things. Let's just think about the transmitter being on this side of the target. So we've got a target, think of it being a plate or something like that. We've got a transmitter like this, and so now the magnetic field is going like this, right? So that's the primary field. And for that part that comes through this way, the magnetic field is coming in right now. We're going to have currents in here that are going to counteract that. So the magnetic field for the primary is coming in like this. That means we need to have a magnetic field, for instance, at the top, that's coming out this way. So then, now my right-hand rule says, it's going to oppose this. So my magnetic field from here is coming out, down, in, and out. Okay, and that's giving rise to this. So let's look at that magnetic field that's coming in like that. If we're sitting up at the surface, so the magnetic field here, the secondary field, goes like this. Okay. So if I'm sitting here with a loop and I say, okay, I've got a primary field, what direction is that? Well, it's coming down like this. And I've got a secondary field like this. So that's coming down. Both in the same direction, positive number. That's what's happening over here. And clearly that decays away. You know, you simply go farther away, then everything just gets smaller. So at some limit out here, everything gets, you know, gets zero. And then it rises up, it's positive, it's positive. But then what happens as the receiver starts to get towards here? Well, as the receiver starts to get towards here, and in fact, if at the moment that the receiver is sitting right above the plate, now the magnetic fields are coming in like this. So my magnetic fields are parallel to the receiver, so there's no flux coming through. So I'm going to get a 0 in my data because I'm just not measuring anything. There's no flux coming through that coil. Okay, so that gives us this guy here. Okay? What is then going to happen if I actually measured something up over here? So I can still imagine that the transmitter is on this side. If now my receiver is sitting over here, now what's going to happen? I've got a primary field that's coming down. But look at my secondary field. It's looping like this. So my secondary field is pointing up. That means I'm going to have a negative value. So when my transmitter and receiver are straddling this guy here, I'm going to have this negative value here. Okay, so now we've got this part. I've got this part. The next thing is, as we move over, I guess one more. If I keep moving this now so that my transmitter gets to be right over top of my target, I'm now also going to get a 0 value, but I'm going to get a 0 value because my primary field is, you know, parallel to this guy. So there's no time varying flux that's going through here. So there's no currents, nothing. So here there's nothing happening. So that means I get no magnetic field that's from here, which means now I'm going to have a 0. And then when I move things a little bit farther apart so that I've got a transmitter and receiver on one side, I'm back exactly to what it was over there, and I could get something close. So that's it, and that's why I told you on Monday that, you know, if you really could sketch this curve out, then you really understand a lot. Because even though, you know, you could just simply kind of draw like, okay, here's a sketch, right? There's 2 zero crossings. But the two zero crossings are happening for very, very different reasons. One, you're not capturing anything with the data because the orientation of your receiver is in the wrong position. This one here, you're simply not igniting the target. So same thing, but very different physical causes. Okay. Good. So that allows us to sketch out what the sort of the structure of that curve was, right? So we got something that looked like this, right? With here the plate sitting down here. But now we have to come back to say, oh, well, we got this in phase and quadrature phase part, and that's where this other diagram comes in. What this does is tell us what the relative proportions are in the in phase and out of phase part. So if I have a good conductor, I'm sitting up over here. So remember this quantity in here was omega times sigma. So if I have a good conductor, I'm sitting up over here. That means that the real part is much larger than the imaginary part. And so when I went out and I look at my instrument's going to give me two numbers. The real part is actually going to look like this, and the imaginary part will look exactly the same, except it's just got a smaller amplitude. So a character of the curve will be the same, but the relative proportions of the in phase and the quadrature are different, and they are governed by this particular image that's here. Okay, so that means that you've got a way of kind of understanding what the character is of the signal, as well as getting some information about the relative strengths of the two numbers. I want to maybe just make one comment back here. One of the things that's really useful, and I might ask you a variant of that on the final exam, is that we've done some sketching out here where we've got a moving system, but I could equally well ask you a whole bunch of other questions. I could ask it, okay, so suppose that you had just a transmitter here, okay, and then now you're going to just leave the transmitter fixed, but move your receiver. So I could do that, right? I could just keep the transmitter, and I could walk a receiver across here. In which case, I would have over here, I would have a positive value that was obtained. I'd still have a zero crossing, but over here I would have just a negative value. Everything is going to be, the transmitter is always going to be on one side and the receiver is on the other. So I'd have a very different signature, even though nothing has happened here. I just have the same transmitter, I have the same currents in here, but it's just what I'm measuring. The other variant that could be asked is, instead of having a receiver that's just horizontal like this, I could say, okay, so what would happen if you had a vertical, a coil that looked like this? Maybe it's worthwhile doing. Okay, so suppose we had this. So we have a transmitter here, and so that's going to give us this primary field that's coming in like that, right? So we've got a current that's coming out here and in here. So now my magnetic field, just like the secondary field, the magnetic field is looking like this. So that's my secondary magnetic field, kind of snaking around like that. So now if I measure, so now what would happen if I measured the vertical component, or if I measured the horizontal component by having my receiver in this vertical orientation? So now, instead of having a loop like this, I'm going to have a loop that looks like this. So first of all, what would that sketch of the curve be? So again, we think about that's our secondary field. Maybe I'll just draw another diagram over here. So here was our primary. So I just want to keep everything the same. Yeah. So here's our primary field that looks like this. So if I'm sitting with a vertical coil, okay, then what would my primary field look like in my vertical coil?
0.
It's going to be 0, right? So here's a case where if I actually tried to do, HS upon HP, I actually don't have a primary field through the coil. I only have a horizontal one. If I just look to see what the secondary signal is from here, right? So instead of doing HS upon HP, if I just said, okay, well, what's my secondary field? Okay. Now, as I'm coming over here, my secondary field is coming up like this, and it's coming through here, and so I'm going to have a very large positive as I get across here, and it's going to be decreasing as I go from back to forth. So the net overall signature is actually going to be something like this. So my point with all of this is that I'd like you just to think about, okay, I've got a transmitter, I've got something here, I'm going to get some currents, now I've got the magnetic fields, and then now I could measure any particular component. I could measure a horizontal component, a vertical component, whatever, as I go across here, and that would give me some information about what's there. Okay, so that's as much as I want to kind of dwell on this. I want to do one more thing here to put in perspective. When we do this survey, we've got a transmitter here, and we've got an earth, okay, that has got some electrical conductivity to it. In other words, the background isn't free space like we've been thinking about with the loops, but we actually have a conductive material here. So I want to now take a look at what the effect of this background conductivity is, because that is actually going to attenuate the signal as we go down. And there's going to be something called the skin depth, which we'd already seen when we did the GPR. And it's going to play a role here too. So imagine we've got something called a plane wave. So a plane wave is just a wave that's kind of uniform in all spatial directions, and it's coming down on this table, and it's just oscillating as it's coming down. So it's a sinusoid that's propagating down, but there's nothing happening laterally. Everything is uniform. So if we look to see what happens in the air for the EM31 frequency 10 to the 4th hertz, the wavelength up here is about 30,000 kilometers. So lambda, well, what's that got here? So lambda is c times the period, or c divided by f, and c is velocity of light. So that's actually a pretty big number. So we've got a wave that's coming down. It hits the Earth, but in the Earth, there's, it's a big conductor. So let's suppose even that you had 10 millisiemens per meter, which is probably pretty close to what the conductivity of the ground is outside. Then everything changes. As this wave comes in, first of all, it starts to travel much more slowly. The wavelength changes, and it also attenuates. So as the wave's traveling in the air, nothing happens to it, doesn't attenuate. But as soon as it gets in here, instead of traveling at the speed of light, it now travels according to this formula, and that means that for this particular case, it's about 3 times 10 to the 6 meters per second instead of 10 to the 8. So it's much slower, and the wavelength, instead of being 30,000 kilometers or 30,000 meters, is actually 314. So there's a couple of orders of magnitude different. So as the wave comes in, it's got a different wavelength, much shorter. It propagates more slowly, and it attenuates with something called the skin depth. So we've seen that before. So delta, it's called the skin depth. Anybody remember what it was? So as a wave sort of propagates in, then what was the skin depth? The definition?
37%.
Right. So if this has an amplitude of 1 at surface, and this is 1 upon E, where E is 2.718. So it's about 35% or something like that of this. Then this depth at which that, this is depth Z, the depth at which it hits that, is called the skin depth. So the skin depth is actually given by this formula. There's another one that we'll use. It's in the GPG. So delta is equal to 500 root rho resistivity upon F, or equal to 500 1 upon sigma F. This is actually a pretty handy formula to know. It just kind of grounds you, lets you know how much things are attenuating. So here's that expression for the skin depth, basically just redrawing what I had already done. We got an amplitude and a depth. And what that means for that wave that's coming in is that it's still oscillating, but that the amplitude is just decaying like this. Okay. So how does all of that play out when you're at the expo site with your EM31? We have a system that looks like this. We've got a transmitter, we've got a receiver, and there's an earth that has got some particular conductivity to it. And the question is, how are we actually sampling that earth structure, and how can we get information from our data out above that? So I'm going to talk about something called a response curve and show you kind of how that works. Do that. So I'm going to write something called phi sub v. So the v is vertical, and the vertical stands for a vertical magnetic dipole. So sometimes you'll see this. VMD is a vertical magnetic dipole. So remember I said that if I have a loop of current, right? So if I have the loop, then that gives rise to a magnetic field that's just like a magnet. So if I had a loop like this, then the magnet is like this. Right? So the magnetic field lines go like that. For that reason, people have chosen to refer to a horizontal loop as a vertical magnetic dipole. So it might be a bit confusing, but try to get over that. So that's what we mean by this. The second is, if that system is sitting here, there's going to be a response that's coming from the Earth, and the question is, at what depth is that response coming from? And that's characterized by this quantity here, which is the response function for the system. So it goes up like this and down like this.